And I'm live. That is cool. Today is 23rd of August 2025, Saturday. And in today's stream, we are going to have fun with fundamentals, which is kind of necessary. And so let's just begin. We will go to ChatGPT and ask ChatGPT what are the fundamentals that are necessary for competitive programming. And we will see what we know about the fundamentals. And the main thing is this fun. We need to have fun along the way. Fun is important. Without fun, we would just drop off. So, what are the required to be really good at particular spelling is wrong. Competitive programming. All right, let's strip this down to the ground reality. Becoming really good at competitive programming isn't about memorizing a bag of tricks. It is about building a layered skill set where each layer strengthens the other. Think of it like martial arts. The flashy moves come after the balance, stance, and reflexes. That makes so much sense. Here are the fundamentals you need. Core programming fluency. Okay, language mastery. You should be able to translate your thoughts into code without friction. That makes sense. Language mastery. Pick one language. C++ is the gold standard. Python and Java are decent but slower at high levels. You must know STL, C++, built-in data structures, and standard idioms. So what do we know about language mastery? Well, we know that at the moment I am reading this book, The C++ Programming Language by Björn Stroustrup. This one, maybe this is not the latest edition. The one that I physically have is edition 4, and this is taking a bit too long. This is going to get there. It is going to be fine. It is going to get there. And yep, let it go there. And then there is also implementation speed. Writing bug-free code fast. Typing isn't the bottleneck. Clarity is. That makes sense. I need to know about the language, the things that the language provides, tools that I can use in a language, which I'm exploring on a daily basis. And then there is implementation speed. If I have a thought, then I should be able to write it faster, right? In a speedy way, and make sure that it is bug free the first time I write it. And debugging reflexes. Right? For me, the debugging is printf debugging. When you print the state of our program at different points in the program to see where it goes away, where it strays away from the expected behavior. Know how to spot off by one errors, input parsing issues, memory bugs, etc. Under time pressure. Without this, you will struggle, even if you know algorithms. Okay, so which part is this? This is the third edition. The fourth edition is also out. So this one is pretty cool. And AT&T, of course, this is by AT&T because AT&T owns Bell Labs, and Bell Labs is the place where Mr. Björn Stroustrup created C++. Murray Hill, New Jersey. And this book is pretty cool. It has a lot of stuff. Currently, the part that I'm reading is STL, but wait, this is a little different from the fourth edition that I have. In the fourth edition, there is introduction to this STL, and then there is a chapter on containers, and then algorithms, which it appears to be here also. Yep, form is liberating. That is the motto. And yeah, algorithms, that is what I'm reading about right now. And I did make a post on this today. Void function. This looks so bad. Let's look at this. What is this function trying to do? We have a function f that takes in list string. Okay, this is very old. This is very old. I have not seen this kind of thing. What is a list? This is fine, a reference, and this is the data type inside string. But list, I guess it is equivalent to vectors. Wait, shit, it is list. It is a doubly linked list. My bad. It is a doubly linked list. So this function is taking a reference to a doubly linked list containing strings, and then we have string const iterator p. Okay, so we did not have auto. We didn't had auto at that point. So okay, we have to literally write the whole type here. Const iterator and const iterator so that you cannot change the value at the thing. Okay, and then find list begin to list end Fred, and if p equals end, then didn't find Fred, and if not, then p points to Fred. That is cool. Okay, so we need to do some language mastery, and we need implementation speed, which is practice, which is practice. Are there some quizzes? C++ implementation quizzes? Are there quizzes like that? Numerous online resources provide C++ implementation quizzes to test and what are they? Do we see some online test and quiz? cppquiz.org, a whole website on quizzes. Let's see that. Yo, CHCP is good, right? Yep. Uh, CPCH, competitive CPHB, I think is a thing. Competitive Programmers Handbook, what the heck? And like set iterator. What is CHCP? Like set iterator. Yep, set iterator. A iterator is a generic class type and it has a lot of smaller children which have inherited the iterator type and have been modified to fit their specific data type to iterate through their specific data type, like you have iterators in vectors and in sets, in maps and everything, in lists. Okay, there is a quiz. We have to, in this thing, output according to the 23rd standard. What is the output of this program? Shit. Okay, I don't know what the 23rd standard. 23rd standard isn't even implemented fully yet. Yep, it is not even implemented. Wait, it's C++ standard in Clang++. I guess it is 20. The latest C++ standard is 23. To enable C23 support, you can use this. But no, that is not what I heard. Yep. How long ago is this? Partial. I guess it is partially available. 23rd standard is not fully available in C++. In Clang++, it is partially available. And in the next year, 2026, we will have a new standard. So that is cool. And let's try to solve what this thing is, what will be the output of this thing. And we are trying to have fun here. And void g. G is a function taking shit. G is a function taking a integer reference and standard out L, and we are not giving any name to that thing. Okay, and this is okay, this is reference L value, and these are two ands, which means an R value. Okay, R value is some temporary variable containing a literal value. So that is why they have L and R here describing that. Okay, then we have a type T, and we have a function T f that takes R value, and we are calling it T. We are referring to that R value using T. Okay, if std is same t and int t. Type t and int t cout 1 and cout 2 and cout 3 and g forward. Okay, I do not know this forward thing. I guess forward would give me a forward iterator or something. Okay, we have to output this thing 42. 42 is the secret to the universe. And then we are calling 42i, which is this is our L value, this is R value. And when we are providing L value to a function that is requiring R value, it can be typecasted. What cannot happen is if a function requires a reference, but you are providing something like this, a literal R value, that is going to give you error, but I think this thing is not going to give you error. The program has a compilation error. Okay, we have choices. So I think this thing is fine. This thing is fine. We are requiring here a R value and we are giving an R value here, an or a R value. And then we are checking the type. So what would be the output? R value is the same as a reference. I think all of all of these would be printed. All of them would be true. All of them should be true. Because when we are using a reference, I think the is same function does not care about a reference. When we are using something like a reference, then we are putting there the actual value and not the fact that we are using a reference. So we are only using the value that is referenced by our reference and not the fact that it is a reference. So this is different from using a pointer in that sense. When you are using pointer, you give a pointer and you have to dereference the pointer when you want to use its value. But with the reference, you are actually using the value and there is no way you can access the reference itself. And that's why compiler can sometimes even optimize by skipping the whole reference part and using the literal value. Okay, I do not know about this forward function, but I can say in this part, I think 1, 2, and 3 should output. But here, this G function is using forward. What is this forward function? Okay, std, stds forward. C++, of course, C++, CPP reference, forward. And 142 will point to 1, then I equals 0 will point to int reference because of reference. Okay, 142 will point to 1, then 42 will point to 1. Yep. And then I equals 0. Then I equals 0 will point to 1 also. I think all of them should be true because the thing that I'm supposing is that when you're using the is same function, what I've read is that these extra bits will be stripped off. These things would be stripped off, this L value reference and R value reference, and we would only look at the fact that these are integers and not the fact that these are references. So I think 1, 2, 3, all of them should be outputted. That is what I think. And then about iterator forward. What does the forward thing do? Forwards L value as either L value or as R value depending on T. Uh-huh. Okay, this takes in type name T reference L value reference, no exception, this will happen all the time, and return R value reference to the same type. Okay, a constant expression for the same thing, taking a L value reference, and if it is R value reference, it will return the same R value reference. Okay, so this thing will make it R value reference, and when we are passing a R value reference, this is the thing that is going to be called. So R will be called in both the cases. So 1, 2, 3 R, 1, 2, 3 R. That is what I'm going with. I don't know if that is correct, but let's see. Incorrect, it seems. Okay. Okay. Try again. Okay, let's see. But that to me seems correct, but that is of course not correct. And why are messages being retracted? That is sad. That is sad. Okay, we have to get this right now. Now, after looking at the definition for this forward function, I am pretty sure that G is going to output R, but it seems like this is not going the way that we are thinking. So 2 R 3, if these ands are not stripped away when we are using the same function, then first here we are providing a R value reference. Therefore, 3 should be called, should be printed, and then R because of this, and then I equals 0. It is a L value reference. No, it will be typecasted into a R value reference because that is what this function takes. If it is an L value reference, this function will not be called. Or maybe this might even give an, will this give an error? Do we have to explicitly, do we R L value references implicitly converted to R value references? That is the question. L value references are not implicitly converted to R value references. Instead, an L value expression can undergo an implicit L to R value conversion, which produces an R value. This R value can then be used to initialize or bind to an R value reference. So will this thing give an error? Because here it is cool. This thing is cool. But here we are not even providing a reference. But it should be converted into a L value reference, which can be converted into a R value reference. So what I'm going on with is 3R, 3R. That is also incorrect. Okay, shit. Hint. Are you sure you want to use the hint? Have you really thought? Okay. Reference collapsing ensures this turns into this, while this stays at as this. But we are not doing something like that, are we? Forward. What is the forward? Maybe we read something wrong with the forward iterator. Forwards L value as either L values or as R values, depending on T. Depending on T. When T is a forwarding reference, a function argument that is declared as an R value reference to a CV unqualified. Okay. I guess instead of CPP reference, C++ would be better. C++. Yep, they have a much better thing. Their documentation is just not updated up to the date. Returns an R value reference if args is not L value reference. If args is an L value reference, the function returns args without modifying its type. So L value remains L value and R value, and everything else just becomes R value. Okay, so with this, I'm going with 3, and then since it is R value already, it should become R value without modifying. If it is, it returns an R value if it is not an L value. And here, this is not an L value, so R value will be returned, which would be R. So 3R, and then for the second bit, I would say 2, because no, I think 3. And then here T is R value in both the cases, therefore it is not an L value, therefore R value, therefore R seems like the answer, but that is wrong. Okay, we do not know about the fundamentals in C++. Shit. Okay, we know that. I give up. Show me the answer. Okay, let's see. It's okay, sometimes you just don't know. At least you gave it a few tries, maybe. Try another one. Okay. Difficulty second level according to C++ 23rd standard. The program is guaranteed to output 1R2L, which is very similar to this thing. 1. That is cool. Explanation. 42 is an R value. I is an L value. That we knew beforehand. How does this impact the template parameter T and the type of T? The first thing to do when reducing a template parameter P is to ignore references. And this is going way over my head. Okay, wait. We have to go for the fundamentals. Language mastery and implementation speed and debugging reflexes. Okay. That would just come by reading about the language and implementing code and algorithmic foundations. Basic data structures, arrays, strings, stacks, queues, sets, maps, heaps, and hash tables. And we can implement all of these in C++, and we know how to implement all of these. They even have iterators, forward iterators and backward iterators for all of these data types in C++. So that is cool. Sorting and searching, binary search. We can do binary search using some invariance, 2 pointers. Yeah, more or less we can practice on 2 pointers. Divide and conquer, we would have to practice on these things. And graphs, BFS, DFS, we know about what this thing is, what this is. Dijkstra for finding shortest path between from one point to all the other points. Bellman-Ford, Floyd-Warshall, Kruskal, Prem, Union Find. Okay, DP and greedy and maths. Okay, in this stream, I would like to focus on maths and get the understanding about maths. Pattern recognition. Okay, maths. Let's go for maths. And where can we read about maths? Here. Okay, in the last part, we did something about number theories. Not in the last part, in some earlier stream. We read about number theory, and that was pretty cool. And now let's go to combinatorics. That is going to be cool. Okay, let's just lock in with combinatorics, because a lot of study is required, and the number of questions I was doing does not match the amount of theory that would be required. So let's go with combinatorics. Combinatorics studies methods for counting combinations of subjects. Methods of counting combinations of subjects. Usually the goal is to find a way to count the combinations effectively without generating each combination separately. That makes sense. If I have a solution and I have some items and I need to combine them in some way, then I there should be a way through which I can calculate how many possible combinations there are without actually making the combinations, thus making it more efficient. As an example, consider the problem of cutting the number of ways to represent an integer n as a sum of positive integers. For example, there are 8 presentations for 4. That makes sense. How many combinations of integers, positive value integers, can I make? Can I use to add up to 4? That makes sense. And this has to be positive, because if it were negative, we could just keep using -1 + 1 -1 + 1, like negative and positive of the same number. And in the end, it would not contribute to the end result of being equal to 4, but it would increase the number of combinations. So that is bad. Now, this is one thing. This is another thing. This is another. And here we are considering 3 + 1 different from 1 + 3. Okay. Those are the 8 ways in combinatorics which we can use to represent 4. That makes sense. A combinatorial problem can often be solved using a recursive function. In this problem, we can define, okay, that makes sense. I think without reading further, I think I should be able to write a function which takes a number like this and returns the solution, returns the number of ways, or maybe even the ways themselves, which we can use to represent a number. Let's do that. Let's do that. Let's write a function for that. We will go to DSA, I guess. Yep, DSA, CD concepts, and combinatorics, ls, and write a new file, find a number of sums.cpp, right? And here in main void, and we would have here a function that will return a vector of vectors. That would be good. Include vector, and using namespace std vector of integers, and find ways. It will take in an integer. Let's call it n, and then call itself. And we can have a global level vector to represent our answer or response. Let's call it, and for int equals 1 till I less than equal to n and I plus plus, we will call this function. And also we would like to pass in the way, right? Push, push. This is, hey, this is cool. This is cool. We can actually say this, that this is going to return a reference to this thing, and we would vector int have our own response at each level, and we are going to call this function. Yes, we are going to call this function, and we will get the response auto resp equals find ways for calculating n minus I, and then when the number that we have added right now is I, and that gives me a few possible ways to get to n minus 1, that is the remaining sum. I will add them as separate ways into my response. Do this for auto x in resp, right? Resp dot pushback, resp dot pushback. First is going to be our number Res dot push back a vector which has I. That makes sense. Push back I. And then in that thing, we would like to expand that vector which we just added. Can we do expand or something? Or can pushback take a range of vectors? Would be x dot begin and x dot end. Okay, we cannot do that. How can we extend a vector? How to extend a vector in C++ with some iterator? Yep, we looked it up yesterday. Insert at this place. More elements dot begin. Okay, insert. We can use an insert. That makes sense. Res dot back dot insert. Insert at which position? Insert at, we only have one element at this time, so insert at res dot begin plus 1, that is the location, or maybe res dot begin is fine. Add x dot begin and x dot end. That seems to be bad. No matching member. Okay, that seems to be very, very bad. Insert. Why is that bad? Original vector. Add to the end of the original vector all of this. Okay, we can use the end iterator, it seems. That makes a lot of sense. Res dot back dot end. Yeah, that is fine. That makes sense. Now we also need some base cases. Some base cases. Some base cases. Now, what is going to be our base case if 1 is going to be our base case? Yep, 1 is going to be our base case. Or if n equals 1, then return vector int with just one thing, 1. Is that cool? That doesn't seem to be cool. We can do res dot pushback 1. Pushback this one vector, else if at some point n is also going to be 0. If not n, then res dot pushback. Then just don't. Then just don't do anything. We can check if if it is not equal to 1, but it is equal to something, paste 6 or 7, whatever, and 7 return res stack memory, and we are returning a reference. Is that a problem? Reference to stack memory associated with local variable res. Yes, res is a local variable, but we are returning its reference so that we do not copy it. We can maybe change that in that case. It is not a reference anymore. Okay, let's go through this. If n equals 4, right? We initialize this thing, n is not equal to 1, and n is, therefore, I equals 1, 1, 2, 3, 4. It will go, I will go from 1 to 4, and resp gets this thing. Resp is going to get a vector of integers for the sum to get n minus I, which is 3, to get 3. And yeah, we can now go into this function call, which will call this function again for 3, which will call this function again for 2, and maybe we can use a memorization, a map. This is cool, of integers of vector of vector of integers called memo. Okay, we didn't import map. Now we have. Okay, and whenever we get a number, if memo dot count for n, if it is, then return memo bracket n, and else we are here. But before returning memo n equals rest. That is cool. Now we have memorization. Okay, our last function call would be when this I equals 3 at some point, when this thing equals 0, right? When this thing equals 0 and yeah, n was equal to 1 and I starts at 1. So this thing would return something empty and we would never go into this thing. And we would never go into this thing, which is sad. Which is sad. We should no, we wouldn't even go there because n equals 0. That is one thing. Okay, I would not like it to become equal to n. This is cool. The last thing is going to be resp or res dot push back the value n. That is the last way to find a sum equal to n. Now auto x equals find phase for some integer n. And what is this n? N is an integer, c in n. We are going to take it, right? And now for auto x, you cannot use x. For auto c, let's say in x, c out c, but that is bad. We cannot print a vector like that, but we can now, since we have this bit of code. So that seems to be cool and feels like that should work. Concepts and combinatorial. Blank plus. There is only one function, one program in this space, and for 4. That okay, we have a couple of copies which we shouldn't have. Nope, we have a couple of copies. We can eliminate those. We can eliminate those. We can, but the thing is correct. The thing is correct. It works. We only have to eliminate those copies which we have there. Okay, why do we get copies? That does not make sense. That actually does not make sense. And I think if we didn't have this bit, it would be slower. But now we have, so that is cool. Return res. If n equals 1, then return just a vector of vectors containing only one element, that is 1. Else if n is something, then do this. When I called this function with n, when I equals 1, right? When I called this function with I equals to 1, It got called twice inside. Find ways. So it got called with 3, which got called with 2, which got called with 1, which got called, which didn't get called. We just got 1 before back from that. And that 1 was appended with 1 from our 2, right? That makes sense. Let's start push back I. We are pushing back I. Why do we have it multiple times? Push back I, right? And then into I, at the back of I, insert this whole thing. Okay, let's, if we do this, this is going to be like, this is going to be messed up. Why is X bad? X is bad because we have this printing thing before. Find number of sum. Let's say for 2, and that is bad. That is for 2. That is bad for 1. 1 does not make sense. I called this thing for 1, and what did I get? I got rs pushback 1. So that should have been returned. Why am I getting it twice? Twice does not make sense. Is it because of this? Right, right, shit. Uh, return res. That makes sense. Clang slash out or 4. That makes a lot of sense. That makes a lot of sense. That makes a lot of sense. And we have this thing. Here there are 8 ways to represent 4 as a sum, and we have found those 8 ways. 1, 2, 3, 4, 5, 6, 7, 8. We can even number them. We can even sort them. Yes, let's sort this thing. Sort x dot begin and x dot end on the basis of their size. Yes, we are having fun on the basis of their size, which with a lambda function taking in a vector of integers a and a vector of integers b, and return a dot size lower than b dot size. All right, that that should be cool. And now numbers for int I equals 1, I less than x dot size I plus plus less than equal to x dot size, and see out I this thing, a little this thing, and then x bracket I minus 1, 0 index. Yep, makes sense. And clang this thing. Okay, 4, we have the 8 ways to represent 4. Maybe sort this in the opposite order. Find number of ways, see out 5. 16 ways apparently to present 5, and for 6, 32. Okay, it is always increasing by a factor of 2. That is cool. That is cool. So for 7, it should be 64. 64. For 8, it should be 128. 128. For 9, it should be 256. 256. For 10, it should be 512. 512. Okay. And for 11, it should be 1024. And it is 1024. So that is actually cool. That is cool. That is cool that we can simply do that. Wrote an algorithm for this thing. A combinatorial problem can often be solved using a recursive function. Yes, that is what we did using. And one more thing, if we didn't use memory, this memory part, if we didn't use this, then it would have taken a lot of time. Let's say for 11. Okay, it is not that slow. 20, it is slow. It is slow for 20. It is taking a lot of time. It took a lot of time for 20. Okay, let's go there and bring back the memory part and let it print. Let's stop that. And now for 20, it should be faster. I think it was a, yeah, it is faster. It is faster than the other thing. It is printing faster, but it is not calculating faster. Plan slash out for 30. It might even overload the memory because it is going to take a lot of numbers, a lot of things, a lot of vectors to represent this small thing. And we have memory enabled. Okay, that is way too out of the league, it seems. 22, that also seems to be way too out of the league. Okay, it is still doable. Doable, that is fine. Now we can move on to the next thing. Combinatorial. A combinatorial problem can often be solved using a recursive function. In this problem, we can define a function n that gives the number of representations for n. For example, equals 8. According to the above example, the values of the function can be recursively calculated as follows, like something like this. That is correct. The base case is f0 function 0 equals 1, right? And 0 equals 1. And because the empty sum represents the number 0, then if n greater than 0, we consider always to choose the first number of the sum. If the first number is k, then there are n minus k representations for the remaining part of the sum. That makes sense. That makes sense. If the first number is 1, then there are n minus 1 ways to represent this thing. Not that many ways, but the value of this remaining part given to the function f. Thus, we calculate the sum of all values of the form this thing where k goes from 0 till n. So that is cool. Not 0 till n. K goes from 1 till n, because if it were to go from 0, we would be calling the same function over and over again. Fn, 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 and that would be catastrophic. It would never end. But I'm not doing that in our solution. So that is cool. Sometimes a recursive formula can be replaced with a closed form formula. Huh. Which is based on the fact that there are n minus 1 possible positions for plus minus signs in the sum, and we can choose any subset of them. What does that mean? Okay, this makes sense. We are just calculating this. Sometimes our recursive formula can be replaced with a closed form formula. In this problem, we have this thing. The number of ways to represent n as a sum of positive integers. There are 2 power n minus 1 ways. If we have n equals 5, then I would have 2 power 4, which is 16 ways, which is correct. Which is correct. For 5, there are 16 ways from 1 till 16 at the end, which is actually correct. And we also have the social network here movie. Okay, that is amazing. And sometimes a recursive formula can be replaced with a closed form formula. In this problem, this thing, yes, why would this be correct? Which is based on the fact that there are n minus 1 possible positions for plus minus signs in the sum, and we can choose any subset of them. What does that mean? Okay, that is actually true. If you only have ones plus minus this positions for plus minus signs in the sum, and we have a subset of them. This thing, first of all, this thing makes sense. Sometimes we can replace a combinatorial formula with a closed form formula like this. But why does it work in this case? What does this mean? We can go to ChatGPT and have a nice chat about why would this thing work. If zoom a little bit, if I have a function that takes in a number n and returns the number of ways that number of ways n can be expressed as a sum of positive integers, then either I could write a recursive function to calculate that with the base case where f0 equals 1, or I could use a closed form formula like fn equals to raised to the power n minus 1. Uh, but why does this formula work? Why does this formula work? That is the question, right? Hello, Roxy, how are you? Wait, shit, this is early for you. This is like shit, you just woke up, I guess. Great question. You have touched on something that lacks respect, that lacks deceptively simple, but that looks what the heck. You have touched on something that looks deceptively simple but hides a lot of structure. Integer partitions versus compositions. Let's break it down. Okay. What problem you are saying? Yes, something like this. Okay, here ChatGPT is considering 3 plus 1 different from 1 plus 3. Okay, 5 is composition. Order does not matter. Yes, here we have 8. Okay, partition and composition, permutation and combination, partition and composition. Okay, your formula 2 power n minus 1 matches the composition, not partition. Yes, why does it work? Why does it work for compositions? Think of n as n ones lined up like this. There are n minus 1 gaps, right? And now in each gap, you could decide cut here, insert a plus, or don't cut here, merge with the neighbor. That makes sense. That makes sense. Do not cut here. merge with the neighbor, right? Each choice is independent. Okay, so that makes sense. That makes sense. When I'm merging two neighbors, I am actually merging two signs together. Example. That makes sense. That actually makes sense. We go to escalator. Please help me solve question 2024. What is 2024? I need to solve 9 more questions within 2 days. I will reach 200 questions. That is very cool. What is question 2024? And have you done sliding window? I think I can do it. Book. Book is just this. I have downloaded it. CP handbook. You can just look it up. CP handbook by CSCS, which is cool. Shit. Yes, I saw your lead code. It looks green. You have done a lot of questions and you are doing questions daily, which is cool. Very cool. Lead code 2024. Well, I can at least look at it and see if I can solve it. 2024, maximize. Okay, it is medium. Let's see. Is this the question? A teacher is writing a test with, okay, yes, okay, let's solve this. Actually, solve this. A teacher is writing a test with n true, false questions, with T denoting the true and F denoting false. Okay, he wants to confuse the students by maximizing the number of consecutive questions with the same answer, multiple truths or multiple false in a row. You are given a string answer key where I is the original answer to the ith question. In addition, you are given an integer k, the maximum number of times you may perform the following operation. Change the answer key for any question T or F, that is answer key to T or F. Change answer key for any question to T or to F, that is set this to T or to F. Return the maximum number of consecutive T's or F's in the answer key after performing the operations at most k times. Okay, I can perform this operation at most k times. So what would I like to have? Prefix sum. Here, yep, answer would be 2. Here, k is 1. Answer would be 2. 3. Yes, I can change any of these T's to F's. Here, k equals 1 and changing this would be fine, and I would have 5. This is somewhat like maximum sum subarray, right? Whenever I see a T, I can increment my counter by 1, and whenever I see a F, I can take that as a -1, right? So okay, I can go through this twice maybe. Once supposing that I want to change F, and then therefore I would like to find the subarray which has the maximum size, but the number of F not exceeding the number of K. And then I can do the same with T, and whichever one has the maximum size, I would go with that, and that would be my answer. So how do we do that? How do we do that? We can, okay, I can start iterating from here. My counter of F would be 0. Then I go to the next one, counter of F is 0. Here, counter of F is 1. So that is cool. We go. And yep. And then I see a new F. My left range changes by to this, and now my size is 3, and I will go as far as I can without incrementing that. And here t equals 1, and is this the question that you were asking about? Yep, okay, that is cool. I tried brute force, but TLE, my sliding window algo, is lacking 32 test cases. Okay, let's see. K equals 1, and here you can change this. Okay, so this should be cool. This should be cool. And let's say here you go first, you can suppose that you are going to change F, and you can start iterating from here and find the maximum subarray starting from this point. You will have a left and right ending, and here let's say you want to change F in your first pass. You would want, so you want to find the maximum size of a subarray which has no more than this k amount of f's in it, and you want to find the maximum size of that subarray. So you start with your left equal to the first and your right also equal pointing to the first number, and then you move right, and here you see we are cool till this point. But here is a problem, and you would also like to have the you would also like to have a pointer to the places where you have seen f's, for which you can use a stack actually. Not a stack, a queue. A queue would be cool because you would like to pop this f off. So yeah, we can do this, we can do this, we can do this, we can do this. Go to decode, and let's end to the code.cpp, paste unknown type, or shit, I can do this directly in lead code. That is also fine without an LSP though. Queue of integers last, right? And what else do I need? L R, L equals 0, L equals R equals 0 at the start, and yes, that should be cool. And I have K, and I have my answer key. When I equals 0, I less than, or and R equals 0, R less than N R plus plus, and MX and MX size, MX size when I am trying to remove T, like initially 0, right? And also current size, and current max initially 0, and current T initially 0, right? And now I would like to iterate if L is initially equal to 0, so that is cool. And R points to the number that is in my list, right? So that is not in my list. That is not in my list. So initially my list is actually empty. My range is actually empty. So if answer key R equals T, I am calculating the amount of T's I have. If it is equal to T, right, I would have to increment my CRT plus plus, capital T plus plus, increment my counter. And now if CR capital T is greater than K, then we have ourselves a problem. Can K equal to 0? No, K cannot be equal to 0, but anyways, this is fine. And now what do we need? CRT greater than K. Now we want to pop left, and so left would be equal to last dot front and last dot pop, we can pop it, right? Yep, we can do that. We can do that. And here also, when we did add this thing, this will point to the place where we have a T. So last dot push R, last dot push R, right? This seems correct. Last dot pop, last dot push. We will keep moving forward and update the size after everything. So I don't think we need current size. No, we need current T. We don't need current size. We can just update CR mx equals maximum of CR mx, comma, what is the current size? My L, my L is pointing to the last T, and my R is pointing to the T that is not included. That is not included. I have to keep my invariance intact. I have to make some changes. Because I would like my length to be equal to R minus L, and I am saying that L is pointing, L should be pointing to the place from where my list is starting, right? So in something like this, if I am looking for T, if my left is pointing at 1 and my R is pointing here, if my R is pointing here, then I should have 3 as my length. And if the R thing is included, right, at the start of the loop, R is not included, but at the end of the loop, R is included. So I will do R minus L plus 1 because to make it inclusive. So R minus L plus 1. And what else? The invariance at the start. Current T. If answer key 0 equals T question mark, if it is T, then 1, else 0. So that we just know in case, right? How is this going to work for this thing? Our current counter CT will start at 1. We would be checking this thing again due to some reason, right? And this would increment the thing. So this is bad. This is bad. Our max range is 1. We can change this to 1. That is good. Now we would go to the second T and we will see that it is T. CTR would become equal to this thing, and that makes sense. We would also like to add last dot push 0 because that is where our range starts, right? That is where our range starts. We would push R also. R is the place where we saw a T. So we have to change this thing to R plus 1. To R plus 1 so that when we want to remove this, we go further, right? So at this point in our queue, we have 1 and 2. Makes sense. 1 is the next place, the place after our first T, and 2 is the place after our second T. That makes sense, and I hope I'm making sense. I thought of the same thing. One time F to T and then T to F. Yep. Then let's see if I can do this. CTR plus plus and okay, R is starting. Yep. At R equals to 1 after the first thing. CTR would become equal to 2, pushback 2, and here we would have, I think we can use something like Cardane's algorithm, but that would be too elegant right now if this would be true. So L equals last dot front and pop up, get the first thing in the queue. and pop it. So we would have L equal to 1, and here we would see the new range where our R equals to 1 and our L also equals to 1, and we are doing 1 minus 1 plus 1, which is 1. So that is correct. That is correct. That is correct, actually. No, shit. K equals to 2. So we will not pop anything off. R would remain at R. L would remain at 0. Where is L initially? L is initialized to 0. L will remain at 0. So 1 minus 0 would be 1 and plus 1 would be 2. So current maximum becomes 2. And then we go through again. R equals 2. It is not equal to 1. So this thing is cool. But this thing would increase. It would become 3. And then R equals 3. Yes, R equals to 3, the last number, and we would have this thing equals 4, and 4 would be the answer. That is cool. Now and this is linear time. This is linear time, so that is cool. We have to do the same thing. Max size T. Shit. MX T. Let's call it MX T and MX T and MX T. T. Right. We can do the same thing for Y. For false, right? Mix F, replace with F, point T, replace with F, and we would have to have our last clear this Q and push 1 onto the thing, right? And everything else should remain same. Ah, replace this with F, right? Right, right. Mx F and a few more things. L equals 0 at the start. Clear the hash, clear the stack Q, and what else am I using? Do I have everything? Okay, Z does not work in this settings, so just return mx maximum of mxf and mxf and mxt. Okay, this is going to work. We have a Q, LR. Wait, this thing is correct. We can. Okay, this thing is correct. This thing is correct. This thing is seems to be correct. Right. Let's see. Or maybe not. Shit. I did need LSP support. R lower than N. Okay. Shit. Okay. My bad. My bad. And N equals answer key dot size. Shit. Last dot clear. Yeah. Clear a U and C++. Erase. Clear. Push. And okay, I can initialize a new queue. Last T, people used to call it, and here we have last T again, and last T, and this is very cryptic. Last T, last T, and I'm not being very efficient with my Vim. Clear this thing. Initialize a new queue of integers. Last f. Wait, I didn't add the stuff that I was supposed to add onto the queue, right? Stuff before this. Push. And where is the t here? Okay. This is my initialization that I need before a loop. I don't need this. I already have this. I don't need this. My L equals 0. Don't need this. MXT, do I have MXF equals 0? Yep. And CRT, I have CRF equals 0. And this, I just have to change this thing. Push 1 and pull. But it would be 1 only if there is the thing that I'm looking for at the first, at that position. Yep. If there is something like that at that position, and if not, then empty. If not, then empty. That makes sense. So I can change this actually. If answer key 0 equals t, then do two things. Make CRT equals 1, and by default make it 0, and also do this. LeetCode does not have really nice support for Vim, but that is fine. If answer key 0 equals f, then last f dot this, and yep, this thing. By default it is 1, and if this is the case, then CRF equals capital F equals 1. So that is 2. Okay, let's see if that works. That would be nice. And I will join again after solving, and we'll let you know if I get a better approach. That is cool. And if I do not get a error, okay. List dot pushback last. Did you mean last in the 35th line? Yep, my bad, my bad. Last f dot pushback. Here also, I'll get an error. Cool. Okay, correct for 2, but not for this one. That is a very horrible output. That is a lot of digits. Why do I not initialize any of them? Why am I getting this massive number? MXF initially equals 1, and MXL never equals anything at the start, right? MXL, no, it is equal to 1. Equals to 1. Let's see what these two are. Cout MXF save MXE. Let's see, and what do we have? Compilation error. Okay, it came because of that. Cool. Why are they so big? mxf and mxt. Am I not initializing one of the variables? Both of them are massive due to some reason. mxf and mxt, both are massive. Okay, mxf starts at 1 in this particular case. mxf, when I am trying to remove f, it starts at 1, right? Because just because. And then current f, current counter for f, which will be 0 because answer key 0 is f. Q last f. I would have done this, but I won't. Okay, it messed up because of f, I guess. Right. For int r starts at 1, it is not equal to f, so we just move. Wait, what? It is not equal to f, so we just move, and f is not, current f is not greater than k. Current f is actually 0, so this is false. So yep, and r is 1, l is 0, that is 2. Cool. mxf should have been 2 here. We can actually track this. mxf, see, it should have been 2, then 3, 2, then 3, then it became 4, yep, and then 5, 5 would have been cool, and 4, 4 because of this. Then we added this number here, it became 5, and then here it should have reverted back to this and should have become 3. Okay. And crf, current count for f, right? F was 0, f became fucking 1 due to some reason. Why was it 1? Right, it was 1 there, it was 1 there, it was 1 at that point, and then last f dot pushback, last f dot front. Let's also output value of L, L, printf debugging, it is called. Yo. Okay, what do we have now? L equals 0 for the first pass, and at some point it becomes very massive negative number due to some reason. Okay, it is because of QE. It just went there at the end. When I went to this F, when makes so much fucking sense. That makes so much sense. CRF minus minus. Shit. Shit. That makes sense. That makes a lot of sense. CR T. T minus minus. Let's see. I guess it might be correct. Yeah, it is correct now. And we can just remove this part. Okay, let's submit and see. Hmm. That is not very good. That is not very good. The performance is not very good. Why is the performance bad? I mean, it is linear time. Maybe I can keep track of this thing in just one loop, combine all of these states, max consecutive answer key. Okay, I can add this question into review or something. Note, no, the star, yep, save, favorite, I guess, yep, but it does work. The approach is not good. Approach is horrible. Look at this. Look at this. Approach is horrible. It takes 22 milliseconds. It takes 20, but we can do something illegal where we can do auto init equal at exit. What was the thing? At exit. I saw this somewhere. Does not take anything. And yes, OS OF stream for display runtime time.txt and add to this thing 0. If this works, it would be kind of cool. Okay, there's some error in okay, because of this, I need a semicolon here. Okay, there is add exit is not a function, add exit is a function. Okay, this is illegal actually. Should not do that. See, this is illegal. This is illegal. Display runtime. This is bad. You should not do this. Can I do this same for the memory? Display memory 0. And okay, init mem. No, it does not work for memory. But this is hack. This is bad. This is bad. You should not do this. And back to our combinatorial stuff. Okay, this was the thing, and we were trying to see why this would be correct. This would be correct if, let's say, my n is 5, then I can represent this using 5 ones, and given these 5 ones, I have 4 places in between. 5 minus 1, 4 places. Now I could choose this sign. I have to find the number of subsets with these 4 values, and if your set has 4 values, then the total number of subsets is going to be 2 power 4. And if your this 4 came by n minus 1, so the answer would be 2 power n minus 1, because I could choose any given sign, and if I am choosing a sign, then I would use the value to its left and then the value to its right. But if I'm not choosing a sign, then I will combine these two values as 1 and I will write it as 2. And I can do this independently for every single sign. So that makes sense, and therefore this thing makes sense. Now on to binomial coefficients. Shit, that is crazy. The binomial coefficient nk equals the number of ways we can choose a subset. Nk equals the number of ways we can choose a subset, right, of k elements from a set of n elements. That makes sense. Subset, right? But we cannot re-choose any stuff. If I have n things and I have to choose k things among them, then at the start I have n options, then I have n minus 1 options, dot dot dot, till at the end I have n minus k minus 1 options, right? Because I used, yeah, yes, this many options I will have. Yep. And this can be written as n factorial divided by k factorial, because divided by k factorial, I guess, or if I were to take this forward, this would be into n minus k. If I were to open this, n minus k plus 1, then this would become n minus k into n minus k minus 1, and so on till 0. And I need to find a representation for this thing. This would be n minus k factorial. N minus k factorial. So n factorial divided by n minus k factorial, it seems, because this, I just want to make sure this is correct. I, among, let's say n was 2, I used 1 here and then 1 here, and the number here I have is n minus 1. So that is correct. Yep, n minus 1. And if I were to open bracket, I can write this thing as n minus k plus 1 plus 1. And the number 1 minus this would be n minus k. And that is the number whose factorial I am looking for. So the answer would be this. When I want to choose k things from a set of n, from a set of n elements, then this is the formula. Let's see if that is correct. Here we have 5, 3 equals to 10, because the set this has 10 subsets of element 3. We can verify 5, 3, 5 factorial something divided by 2 factorial, because 3 minus 5 minus 3 is 2, which is 5 into 4 into 3, which is much more than 10. This is much more than 10. So something went wrong. At the start, I have n choices. Then I have n minus 1 choices. 3 elements, k equals 3. 3 elements, I'm choosing 3 elements. I have n factorial, then k equals 3, and 5 minus 3 is 2, 2 factorial, 5 into 4 into 3, 26. It turns out to be 60, which is very, very wrong. Subset, subset. Shit, shit, that is not how you calculate subset. Number of sub. Shit, okay, yes. Shit, you need 3 things, right? When you are choosing 3 elements. For the first element, you have n choices. Then for the second element, you have n minus 1 choices. For the third element, so this seems to be correct, 5 into 4 into 3. Then for the third element, you would have n minus 2 choices. So why would this be correct? If I have 1, 2, 3, 4, 5 things, I can at the start choose anyone. but they don't overlap. I think here we are choosing 1, 2, 3 as distinct, as same as 1, 3, 2. The order does not matter. If the order does not matter, then I need to know. Yep. If and then this would be one thing, right? This would be the permutation. This would be the permutation. And to find the combination, I have to divide this by, okay, how many ways can I arrange these three numbers? That would be 3 factorial. So that is cool. So 5 factorial divided by 2 factorial into 3 factorial. This part here gives me the number of permutable ways in which I can arrange 3 things out of 5 things. And this gives me within those groups of 3, how many ways can I represent those groups of 3 so that I'm only choosing one of those representations. So this would turn out to be 5 into 4 divided by 2. 1, 2 from this 2, which equals 10. So cool. That is cool, which is the correct thing. Cool. Formula 1. Binomial coefficients can be recursively calculated as follows. Okay. Binomial coefficients can be recursively calculated as follows. We have this thing. For example, okay, what is this notation? I do not understand this notation. Binomial coefficient, this equals the number of ways we can choose. Okay, okay, this just means that, okay, n would be how can I choose from n minus 1 elements. How can I choose from n minus, let's say I made one of the choices, then I have n minus 1 elements remaining, and from them I have to choose k minus 1, right? And what is this? How many ways to choose k elements from n minus 1 elements? Why do I have to have to calculate this? The idea is to fix an element x in the set. If x is included in the subset, we have to choose k minus 1 elements from n minus 1. If x is included in the subset, we have to choose k minus 1 elements from n minus 1. And if x is not included in the subset, we have to choose k elements from n minus 1 elements. Okay, okay, that makes sense. The base case for recursion are this, right? When I do not have to make any choices, then 1, and when I have to choose everything, then also 1. Only one way, because there is always exactly one way to construct an empty set and a subset that contains all of the elements. Okay, this thing makes sense. Yep, this is the formula that we calculated. Another way to calculate binomial coefficients is this. There are n factorial permutations of n elements. We go through all permutations and always choose the first k elements of the permutation in the subset. Since the order of the permutations in the subset and outside the subset does not matter, the result is divided by k factorial and n minus k factorial. Shit, that is a very distinct way to look at this. If I have n elements, 1, 2, if I have, let's say, 5 elements, 4, 5, and they can be arranged in different permutations, a lot of different permutations, and I need to choose k equals 3 elements from them. Let's say from all of these possible permutations, this is a lot of permutations. Let's choose only three elements and say we want to choose two elements from given set of three elements. This is one permutation, 1, 3, 2. This is another, and 2, 1, 3. This is another, 2, 3, 1, and 3, 1, 2, and 3, 2, 1. These are all the permutations of this set with three elements, and we want to choose two letters, two elements from this set of three elements, and we want to find out all the ways in which we can do this. Now, when I have two numbers in a set, since this is a permutation, I will have 3 and 2 as well as 2 and 3, but I want to count it only once, so I will have to divide this whole number, which is 6, this 6 thing, right, by the number of ways I can arrange two given elements, which is going to be 2 factorial. And when I do have this thing, there will be, let's say if there were other elements, then they could have different permutations even for the same 3 2 and 3 2. So I want to also divide this result by the permutations that these remaining elements could have. Therefore, since I have total n elements, this gives me the total count of permutations. I need to divide this with these inner arrangements, which are k factorial in total, and then the arrangements of these elements which are outside and not a part of our current are not part of the numbers that we are choosing, and that would be n minus k factorial. Okay, that is a cool way to look at this. That is a very distinct way to look at this thing. That is cool. Properties for binomial coefficients, like this thing equals to k minus 1 because you just switch, right? K becomes n minus k and n minus k becomes k, so the whole thing is the same, right? Makes sense. And because we actually divide a set of n into two subsets, the first contains k elements and the second contains n minus k elements. The sum of binomial coefficients, the sum of binomial coefficients is this thing. The total, oh shit, makes sense, makes sense. I guess that makes sense. The number of ways I can choose zero elements, the number of ways I can choose one element, the number of ways I can choose two elements, and so on, would be equal to the number of ways I can choose any subset. The reasons for the name binomial coefficient can be seen when the binomial a plus b is raised to the nth power. A plus b is raised to the nth power. Binomial coefficients also appear in Pascal's triangle, where each value equals to the sum of the two above values. That is true. Okay, and when I have a plus b power raised to the power of n, then this is how we go. Okay, I would like to write this formula down once so that I remember. I have read this formula before. A plus b power n would be equal to binomial coefficient, or instead of this we can write this as a summation, which would be much better. We can write this as summation I starting at 0 going till n, summation of n I binomial coefficient into a power I and b power n minus I. That should be correct. And is it even given? No, it is not given in the summation formula. in the summation way, but that is how it goes, right? Because you have 0 power 0 and n minus 0, and for 1 power n minus 1 and 1. That is cool. Summation. Can I actually write a function that would calculate this whole thing? Okay, that would be cool. Still running. Process, if you close the terminal, the process will be killed. Why would I like to close the terminal? Tmux kill server, tmux set, and tmux attach t, let's call it DSA combinatorics. Let's n binomial.cpt, a function that would return a long and binomials, integer a, integer b, and integer n. What it is going to do is run a for loop for int I equals n less than equal to n I plus plus initially equals 0 and return ret. And what do we have? Our formula was something like this. Uh, Binomial coefficient of n I multiplied by a raised to the power I multiplied by b raised to the power n minus I. Can do that. So we need to find ni factorial. I can write a separate function for this. Not bino. Yeah, let's call it bino. It takes in int n and int k, and let's give this thing a sort of memory. Map int, map is storing a integer, a pair of integers for values n and k. Wait, I would have to calculate factorial of stuff, so I do not want to do this again and again, keep running a loop. So I can do this integer to long fact include map. Yep, and using std. And for this thing, what is the value of this thing? Value of this thing would be n factorial divided by k factorial into n minus k factorial, which would be, I can write a factorial function. Shit. Okay, fact memo and a factorial function for integer n. First, I will check in the memo if fact memo bracket n, or I can just check it like this. This would also be fine. If it is, then return fact memo for n, else for int I equals 1 I less than equal to n I plus plus, and res equals 1 and res multiply by equal to I. Start with 2 and return res, and before return fact n equals res. Fact memo res equals n, and now res equals fact n divided by fact k into fact n minus k. Return res, and this should be in range. Now I have a thing to calculate this thing. That is cool. Now summation res plus equals multiplication of three things, binom of n comma I multiplied by power a raised to the power I multiplied by power b raised to the power n minus I, and return the result. Int a, b, and n, cn a, b, n, and then right, c out a, b, n, c out in this thing a plus the thing plus b brackets raised to the power n space equal to space binomial. Shit, there is a thing called binomial distribution that is very cool. Binomial a, b, and n. Combinatorics, Planck plus, and we have binomial dot slash out for what? Some equation that we can solve ourselves. Let's say 2 plus 3 power 3, that is just 125. Let's see if 125 is returned. 2, 3 power 3, 125. That is cool. That does work. And of course, it would work for some bigger values. 3 and 6 shit. 3, 6 plus for negative shit. Okay, it is a problem for negative values. That makes sense. If I have negative value powers, what would... Okay, it does not, my program will not handle something like this, but positive value it will. This thing should return 81. 3, 6, 2, 81. Cool. 9 square is 81. 9. We can now move on to this thing, boxes and balls, which makes a lot of sense. Just reading this makes a lot of sense. Boxes and balls is a useful model where we count the ways to place k balls in n boxes. K balls in... Okay, we should be able to derive a formula for this. Wait, isn't this just exactly equal to binomial coefficient, right? This is similar to choosing, given n elements, we have to choose k elements, right? And those key elements would be the places where we would add our balls. And in each box can contain at most one ball. Okay, each box could also contain two balls. Okay, that is a bit different, and we should be able to derive a formula for that. We recount ways to place k balls in n boxes. Each box contains at most one ball. For example, n equals 5 and k equals 2, there are 10 solutions. This is directly binomial coefficient. Okay, I would like to delve into why it is called binomial coefficient. I think at one point I did some research on this, why it is called binomial coefficient, but I forgot. But we will have to do it again then. Okay, if we can put two balls, if a box can contain multiple balls, that is crazy. If a box can contain multiple balls, then also it is easy. Then also not easy, but let's say we have n boxes and k balls, and if a box can at max contain two balls, or any if a box can contain any amount of balls, then we need to do this n binomial coefficient with 1 plus n binomial coefficient with 2 plus dot 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 plus n binomial coefficient with k. So shit, it is more complicated than this. When you No, this is not more complicated than this. When you're choosing, this is the scenario in which you can put only one ball in one box, and this is the scenario in which you can put all of your balls in a single box. And the answer for this thing would be n factorial divided by n minus 1 factorial into 1 factorial, which is just equal to n. So you have n choices. You can choose any of the box and put all of your balls in that, which is not a good idea, but this is what we are going with. And then 2, which means this is more crazy, okay? Because this thing will return the number of ways you can choose two boxes. But within those two boxes, there are multiple ways you can arrange those K balls. Shit. Let's say you have this thing will give you the number of ways you could choose two boxes. Now you would have to multiply this thing with something. If you have, let's say, three balls, then in these two boxes, you could put these balls like this. One box has these balls, one ball, and the other has two balls. And one configuration would be this. And these two are different because the boxes are different. And now if the number of boxes increases and the number of k, let's go with k equals 5. If k equals 5 and you are choosing two boxes, if k equals 5 and you are choosing two boxes, then how many ways are there that you can put 5 balls into two boxes, and any box can contain any number of balls. So 1, and you put all the balls in the other box. That is one way. And now you pop one ball off, put it here. That is another way. You pop one more ball off, put it here. That is another way. You pop one more ball off, put it here. That is another way. So in total, 4 ways. Yep, 4 is the answer. And that is because you had two boxes, first of all, and you had 5 balls. If you had 6 balls, then for two boxes, you would have 5 choices. It would be 5. Now, if you have 5 balls, let's go with if you have 4 balls and 3 boxes. If number of balls equals 4 and number of boxes is 3, you could put the balls like this, and this is mandatory. You have to use these balls, and then there would be one ball roaming around. You could put it here or here, and this would be 3 choices. So the number of balls that can go around anywhere would be n would be k minus the number of boxes, which let's say is I. K minus I is the number of balls that can go anywhere. And let's say for the first box, you have k minus I choices. For the second ball, for the second box, but that no shit. Since you have this many balls and you can put them in any of these boxes, among these balls, the first ball, every ball would have three options. So three, which is the number of boxes power k minus I. This should be the answer. Number of remaining balls, extra balls that can roam free and they have I choices. So I into I into I into k minus I times. So in our original formula, some stuff would change. Number of balls. Okay. We would have our answer equal to a summation, which does not look like a summation at all. We would have a summation I equals 0. No, you have to choose at least one box, right? At least one box, and I will go till k when you have chosen all the boxes. So when you have this many boxes, how many ways can you choose I boxes among n total boxes is n I binomial, and among those I boxes, how many ways are there to represent to put k balls? It would be, since you have eyeballs, yes, you have eyeballs, and how many, no, you have I boxes, and how many balls are remaining? The number of balls that are remaining is k minus I. So this should be the answer. See, it should be around somewhere. Okay, let's read this. Okay, there are 15. Okay, we can use our formula to calculate when n equals 5 and k equals to 2. Let's calculate. In this formula, we have to put n equals 5 and k equals 2. So I will go from 1 and 2. We would have only two terms to find summation of 5, 1, and 1 power anything is just 1 plus 5, 2 binomial coefficient of this thing, 2 power 3 because 2 power 0, shit, which is also 1, which is also 1. 2 power 0 because we are subtracting from k. Now, what is this thing? This is 5 plus what is this thing? This is 10. That is 15, which is the correct answer. That is cool. It is 15, which is the correct answer. So our formula is correct, which is cool. And then the process of placing. Yep. The process of placing balls in the boxes can be represented as a string that consists of symbols O and an arrow. Initially assume that we are standing at the leftmost box. The symbol O means that we have placed a ball in the box, in the current box, and the symbol right arrow means that we move to the next box to the right. Okay. Using this notation, each solution is a string that contains k items. The symbols O n minus 1 times, n minus 1 times, and the symbol O, k times the symbol O, and n minus 1 times the symbol this thing. Because if you have one box, all the balls in one box, you can just, then you would have n minus 1 choices to shift them to the right. For example, the upper right solution in the picture, this thing would be two balls at the start, then push them right, right, one ball, put it to the right, and then one ball, push it to the right. This is the number of key. For example, the upper right solution in the above picture corresponds to the string this. That is, you went from initially you are here, right? You start from here, but you do not put a ball here. You go twice to the right. One time you are here and then here. Now you are here and you put a ball here. That is cool. Now you go to the right once more, and you put a ball there, right? And then you go to the end. Now you are at the end. That makes sense. Okay, and the number of O's equals K's. We have K number of O's, and how many arrows we have? We have n minus 1 number of arrows. Uh, So n minus 1 number of arrows and k number of O's, which is simply k plus n minus 1, k plus n minus 1, which is the total length of the of this string. And from that we are choosing k things, choosing k places. Those would be the places where you are putting the zeros. That makes sense. Hmm. Scenario 3, each box may contain at most one ball, and in addition, no two adjacent boxes may contain a ball. For example, when n equals this, then there are six solutions. It's this. Okay, that is interesting. In this scenario, we can assume that key balls are initially placed in boxes and there is an empty box between two adjacent balls. The remaining task is to choose the positions of the remaining empty boxes. Choose the position of the remaining empty boxes. Should that makes a lot of sense. Shit. Okay, if you have n equals 5 and k equals 2, you have n boxes and 2 balls, then what you must have is a box containing a ball, then an empty box, and then a box containing a ball. And now you have two boxes remaining, and you can put these box at any of this here, 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 and here. So how would you say how many choices you have? You can, so 2 power the number of places, and the number of places would be, wait, you have, right, k is the amount of zeros you have, and right, k is the amount of zeros you have. If you have had one more k, you would have two more choices. So 2k minus 1, I guess. 1, 2, 3. And initially you had this, and you had 1, 2, 3, 4 choices. 6 minus, and that is bad. Minus 2. 2k minus 2 choices. Do you have that many? Nope. When I added one more, I did add 2. So 2k minus 2 choices. 2k minus 2, which is just 2 into k minus 1 choices. 2 into k minus 1 choices. When k was equal to this, then you had 4 choices, because should k is equal to 2. My bad. So 2k minus 1. 2k minus 1. Here you have k equals to 3. and that would be 6 minus 1, 5. 5 is wrong. 5 is wrong. You have 1, 2, 3, 4, 5, and 6 choices actually. It is just 2k. My bad. No, no minus 1. 2 into k, because this made two choices available and this box made two choices available, and every ball made two choices available. So 2k is the number of choices, and the number of boxes. The number of boxes would be interesting. 2k is the number of choices that you have, and this would be raised to the power of number of boxes that you have, and the number of boxes that you have would be 2k minus 1. 2k minus 1 box, because two boxes need one box in the middle. So 2k minus 1. So 2k raised to the power of 2k minus 1. That just looks crazy. Why don't I need n that is going to be subtracted from n? So 2k power n minus 2k plus 1. So that is cool. And in our example, we had n equals 5 and k equals to 2, which would be 4. I messed up at some point. Let's see. 4 raised to the power of 5 minus 4 plus 1, 2, that is 16, and 16 is a lot. 16 is a lot of choices. We have the answer equal to 6. 16 is a lot of choices. Yes, because the boxes are identical, I have to divide it with some value and also multiply it with some value, because 6 is a multiple of 3 and it does not matter with which number I divide 16 by, I will never get 3. It's bad. Hello, bro. Captain, how are you? Okay. So I have a number of balls and a number of boxes, and I want to arrange the balls into the boxes with this given constraint that a ball, a box containing a ball must have an empty box in the middle. So this is the configuration that I must have in our just example where n equals 5. We have n boxes, 5 boxes, and we have 2 balls. Then what we must have is a box containing a ball, and then a empty box, and then a box containing a ball. And I have 2 boxes remaining, which I can place anywhere. I have 4 choices here, 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 or here. 4 choices to place these 2 boxes. So for the first box, I have 4 choices. For the second box, I have 4 choices. To For the first box, I have 4 choices. That makes sense. And then for the second box, I have 4 choices. That also makes sense. No, it does not, because these two are not separate choices. These are practically the same choice, right? Yep, this is practically the same choice. So in total, I would have 2k minus 1 choices. 2k minus 1 choices. Yep. So my number of choices has changed from 2k to 2k minus 1, which is going to be 3, and 3 raised to the power of 2 is 9, which is wrong. So I also have to do some subtraction, some division, which is going to be by 3. Yep, it's going to be by 3. Now I have 3 places where I can put 2 boxes. The first box has 3 options, and the second box also has 3 options. But the first and the second box are not different. So I have to divide this by 2 factorial. Yep. So 3 power 2 divided by 2 factorial, which is 4.5 and wrong clearly. I have a number of places where I can put my balls. Does this make sense? Hello, put up beak. You are also in the server. I saw you. Okay, this is correct. At least this part where I have 3 choices, that is correct, right? And the fact that these 2 boxes are similar should remove the boxes. Yep, I have to remove the permutations from these boxes, and also since I have this box is also similar to these boxes. Yep, this box is also similar to these boxes. That should be calculated in the permutation itself. 2 factorial. 2 factorial. That was not a very beautiful 2. Okay, let's look at the thing. Scenario 3. Yep. In this scenario, we can assume that K balls are initially placed in boxes and there is an empty box between each 2 adjacent boxes. The remaining task is to choose the positions for the remaining empty boxes. Yes, that is what we are trying to do. There are n minus 2k plus 1 such boxes. N minus 2k plus 1 such boxes, right? What did we have? We had n minus 2k plus 1 boxes. So that is cool. N minus 2k plus 1 boxes, such boxes, and k plus 1 positions for them. K plus 1 positions for them makes sense. Yep, makes sense. K plus 1 positions for them instead of 2k minus 1. Yes, but for k equals to 2, that is the same thing. 3, both of them give 3. And yep, then we have this using the formula of scenario 2. The number of solutions is this. We can use the formula of scenario 2 here, and the formula that we calculated in scenario 2 is this. K plus n minus 1 is hmm, we have k plus 1 positions for n minus 2k plus 1 things. Let's say we have n positions for k things. N positions for k things. That should be n by k factorial and n by k binomial. No. That shouldn't be that. N minus k plus 1 because we added k plus 1. So this is something. Okay, I would like to look at why we call this binomial. Like why binomial fraction, binomial coefficient. Now I am in the middle. That is cool. Okay, in the not binomial, binomial coefficient. Why is it called so? Good one. Let's see. The name binomial coefficient is not arbitrary. It comes straight from where these numbers first appear. Okay, the binomial theorem. Take a binomial expression, example, something with two terms. Binomial, two terms like this, a plus b power n. That is binomial. Okay, binomial expression. Okay, and when we are taking its coefficient, then it is binomial coefficient. Shit, that makes a lot of sense. That makes a lot of sense. Why are they written like this? Yes, because the binomial coefficient in this extension is this, which is the number of ways to choose k b's out of n factors. That that makes sense because I have in total n factors, and how many of them are going to be a and how many of them are going to be b. That makes sense. How many of them are going to be a and how many of them are going to be b. That makes a lot of sense. Shit. Does that make sense? Yes, it seems to make sense. So the coefficient part comes from the binomial part coming. Yep. Okay, so that makes sense. We have binomial expressions which are represented as a plus b power n. This is a binomial expression. Why binomial? Because we have a and b, two things bi. And if we want to represent this as something, we can write as a plus b, then into a plus b, that thing, into a plus b dot 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 multiply by a plus b. How many times? N times. N times because we have power n here. And among these, we could choose n by k ways to choose a k times and to choose b n minus k times. Makes sense. And the coefficient of this thing is called binomial coefficient, whose formula is n factorial divided by, this is bad, k factorial into n minus k factorial. That makes sense. I suppose there are total n permutations, and yes, I am switching between frameworks. Here we were referring to how many times we can choose this, and now to calculate this formula we are changing our reference model to permutation. And here we have n factorial permutation of the whole n thing, and we can choose the first k elements from all of those permutations, and from them we are eliminating all the number of permutations within those k numbers and the number of permutations with the rest of the n minus k numbers which we are not choosing. Numbers or elements does not matter, depends on the set. Yep, set like this, set as in Russell's paradox set. There's Catalan numbers. What the heck? Shit. So that is cool. Multinomial. shit, equals the number of ways we can divide n elements into subsets of sizes. This, which is cool actually, because here I could say that I am dividing the numbers into k, into one set of k elements and into another set of k n minus k elements. That makes sense. And if I just add a few more k's, I would have k comma 2, right. But this would be equal to n k1, because k1, because k1 plus k2 has to add up to kn. So this is nothing special, but this thing n k1, when we have a multiple, a few things, k3, where addition of these threes equals n. If we have something like this, then the formula would be n factorial divided by k1 factorial into k2 factorial into k3 factorial, and that is cool to remember. If I have n total things and I want to distribute them into subsets of size k1, k2, and k3, this is how we do this. And this thing is called lot shit. This thing is called multinomial co coefficient. Multinomial coefficient. Okay, makes sense. Catalan. Cat. I've heard Catalan, not just in terms of numbers, but somewhere else. Roman league. No, not possibly. Catalan. Isn't Catalan a car? Caladan. 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 Planet and Dune. Yep. Caladan, not Catalan. I've heard Caladan. It looks like this. Shit. It is called Dan as a nickname. Caladan. Later renamed. Shit. Okay. Okay. This part later renamed Dan. I have not read past volume 3 of Dune, so I wouldn't know that if it was. And I guess it's been 2 hours and 28 minutes. And I guess, unfortunately, that would be the end of today's stream. It has been, it hasn't been quite long. 2 hours and 30 minutes is not a very long time, but yeah, at least I showed up. I guess that matters. Yeah, that would be the end of today's stream. We did some combinatorial things and some other things also. Yeah, that would be the end of today's stream.